Yo, what's up? All right, it's me again, and I already have a Wikipedia article up, ready to go. Usually, I have the web browser just on the standard Tor page, showing you uh, nothing, just the blue Tor screen, and I figured I'm gonna start by just having some kind of interesting thing up for each of my videos to get the discussion motivated. Okay, so I decided to start today by talking about the proton pump. Well, I'm not going to talk about the proton pump today. I just wanted that up there, and I think, you know what? Let's take a look. Get what is, the proton pump. We want to take a look at this. We need images first to work from. Okay, so I don't take credit for any of these images, obviously. I just found them on Google, okay? But, no, I didn't want to go to that site. I just, gosh, annoying. Proton Pump GIF, okay. You know what? All these are lessons learned, so when I actually get good at doing these videos, let's look at, this is ATP synthase. This is basically how ATP gets synthesized from ADP, okay? And ATP is used for pretty much every single cellular process everywhere that requires some energy input. I didn't talk too much about ATP, but I figured kind of like everybody knew about ATP, but I have talked about it a little bit. Let's just go over it again, because I've talked about, the other day I talked about aquaporins, okay? And aquaporins are water channels within a cell. They're proteins which allow water to more effectively transport inside a cell, okay? Because water can come into the cell passively, but in small amounts due to the repulsion and due to the attraction of the water molecules to the hydrophobic heads outside of the tail, outside of the cell membrane and within the cell membrane. So in order to effectively go through the cell membrane in any large quantity, you need some sort of specialized channel that doesn't get water molecules stuck on its surface like the cell membrane does. So that's basically a passive transport mechanism, okay? So what am I talking about? Active transport, passive transport. Passive means, I talked the other day about concentration gradients, okay? When concentration gradient is one of the most basic forms of motivated movement in nature. It's called entropic motivation, and basically it's a force. It's a motivation for movement for systems and for particles in systems that just happens when there happens to be a larger amount of particles in a space, because those particles by default have kinetic energy, which diffuses to all other particles and will just move towards other areas that have less particles by default of the same kind. So, or of any kind actually, but let's stick to the same kind for now. So that's called passive transport, because basically there's more things inside a cell versus outside a cell. Those things will want to go outside of the cell. Let's start with passive transport. Right? So the inside, okay, so this is a good example. So that passive transport, and then passive transport also works in the opposite direction, right? If there's a lot of things outside of a cell, they'll want to go inside of a cell, okay? That's the natural concentration gradient or chemical gradient that exists within a cell. Passive transport, again, requires no energy, no ATP. It will just happen, right? Passive transport also is blocked typically for many reasons, because, for example, we don't want water to just passively transport ad infinitum into a cell. We need to control the passive transport of water into a cell and outside of a cell, right? Because otherwise the cell will shrivel up if there's less water in it, right? Which is the problem with throwing cells in hypertonic solutions, right? Due to osmosis, the water will leave from the cell to the outside hypertonic solution, which has more solute, which is again another passive transport mechanism, and the cell will shrivel up or plasmolyze, okay, in the case of plant cells specifically. The passive transport mechanism is actually it's often balanced by electrical. There's two passive transport systems set up in a cell, right? There's the chemical passive transport system, which is due to concentration of a certain chemical or ion species outside of a cell versus inside of a cell, there will be a concentration gradient. And then there's a passive transport mechanism due to charge differences, okay? Charge differences create a electrical gradient, right? If there's a lot of charge on the left, that charge will want to go to the right because there's a potential energy difference between the right and the left. And things will always want to go in a system from a tendency of high energy to low energy. Whatever the energy of the system can be minimized, wherever you can minimize the potential energy of the system, that's where action will occur to allow that to happen, okay? And that just happens, non-energetically, right? The same way as passive transport does. The same way as diffusion does. So diffusion and electrical resolution, you can think of two forces, naturally occurring entropic forces, in the world. So here's the deal: both of these types of forces are occurring constantly in a cell, right? And a cell is trying to balance these forces. So why are electrical forces occurring on a cell? Well, a cell has a lot of ions outside and inside of a cell, right? Outside of a cell, you have a ton of different ionic species. You have sodium, you have potassium, you have calcium. Inside of a cell, you have sodium, potassium, calcium, etc. Those are your primary ion classes. You also have inside of a cell a large buildup of other types of anions, like amino acids. Okay, these are larger, bulkier anions that can't simply just squeeze easily out of the phospholipid bilayer. Okay, none of these can. Actually, think about it deeply, right? The phospholipid bilayer is why life can occur, right? So a cell spends and I learned this not too long ago, cell spends most of its time and energy balancing these two types of transports, because the transport of ions, right, is really what allows everything else to occur, okay? A cell needs to maintain its membrane potential. What's the membrane potential of a cell? So a cell, because think about how a capacitor works, right? Like capacitor animation. Let's see, capacitor. Okay. This may be familiar to you if you're electrically minded person. You should understand capacitance, though, to really appreciate that. But basically, capacitance is the buildup of charge on one side of a plate, and those plates are separated in distance. Therefore, there's an equivalent buildup of charge on another side of a plate. Okay, so if you have an electrical circuit here, right, and then you have this plate that's separated by some space, as electrical current electrons go to one side and build up on one side of the capacitor, or one plate of the capacitor, because of the need to balance this charge difference, right? Nature will automatically allow positive charge to build up on the other side. Okay, like you always have to. You can't create energy from nothing, right? Like there's going to have to be an electric field that's generated here, and that electric field is maintained by a difference in charge from negative to positive. So that's basically, there exists a electrical potential difference within this capacitor, right? Okay. In any element, there exists an electrical potential difference, but in the case of a resistor, that there's no impedance. The resistance, the impedance to flow is. I don't want to get down that path, because it's just going to go away from biology, right? We're going to go into basic electricity, but let's go back to biology for a second. Okay, so there is an electrical potential of charge that's built outside of the cell versus inside due to a difference of potassium ions, for example, inside of a cell versus outside. So a cell typically has a much larger concentration of potassium inside than outside of a cell. So what will that mean? If there's more potassium outside of a cell, right, or inside of a cell, the cell will want to there will be two processes in effect to get rid of that potassium, right? Because there's more potassium outside, um, inside, right? There'll be a concentration gradient of potassium to go outside, okay? So when potassium goes outside of a cell, potassium exits through a potassium leak channel. Potassium can actually passively transport out of a cell, okay? But the thing is, as potassium goes outside of the cell, the charge buildup normalizes, right? Because let's go to our old friend JS Paint. And I might get a few of these things wrong. I don't think I have any of this wrong right now, or maybe I do, but eventually I'll get it right. So let's call this the cell wall. This is called potassium. And we should specify, this is a positive charge, but this is specifically because it's a potassium. I'm drawing potassiums here. Specifically because these are potassiums, it's important to take into account their concentration gradient, right? I'll say K, right? So basically, by default, all these guys want to leave the cell. They can't leave through the phospholipid bilayer, right? Because the phospholipid bilayer will, have an electronic interaction with them, which either repels them or prevents them from. But whatever the interaction, or attracts them, but whatever the interaction, they cannot penetrate the phospholipid bilayer. So they'll have to go through a specially activated channel, right? This is, typically called, I've heard it called a potassium leak channel. Okay, so the potassium goes to the outside of a cell, right? But as the potassium goes to the outside of the cell, the charge difference, right? Charge difference becomes less notable. The delta, you can call it delta C, right, becomes less noticeable, and therefore the electrical gradient gets weaker, right? Once there's an equal number of charges on one side of a cell versus the other side, then there's no electrical gradient at that point, right? So the thing is, potassium will leave a cell to balance out its concentration gradient, but it will also do that until its electrical gradient is satisfied, okay? So they usually say something like potassium has 150 millimolar concentration inside a cell, and 20 millimolar, let's say, I forgot the exact number, outside of a cell. Okay, so that concentration is the concentration gradient. Now, here's the thing, right? Potassium does not only leave through a potassium leak channel, okay? We also have to consider it's one type of transmembrane protein, right? Transcellular membrane protein that allows transport of substances. We also have the most famous example, the one that was discovered, I believe, when was this discovered? In the 1960s by a scientist named Clark. I forgot his name, a biologist, but anyway, it was flux. It's called flux biology, or flux transport in biology. Not to go too crazy, there's something called the sodium potassium pump, or Na plus K plus ATPase. ATPase. Okay, it's ATPase or ATPase or whatever you want to call it. This is, so while one is a form of passive transport, this is a form of active transport. So why active? So you have Na outside of a cell, right? And you have Na inside of a cell. So this Na will bind to this, to the so-called active sites of this transmembrane protein, right? And it will bind here. And then when three Na molecules bind, the the protein is loaded, right? So the thing is, this protein, the purpose of this transmembrane protein, this carrier protein, is to carry sodium outside of the cell. Okay, now this thing is carrying things, sodium outside of the cell against its concentration gradient, right? Because there's more sodium inside of a cell than outside of a cell, or there's more sodium outside of a cell than inside of a cell. So why would you want to expel sodium from the cell naturally through diffusion? You need to expel it through active transport mechanism. So what does that mean? That means that in order to get this working, you need to load it with ATPase, right? You need something that will ATP, sorry, not ATPase. You need something that will trigger it. That's why this is in a class of proteins called ATPases, because phosphorylation of this protein using an ATP substrate will cause it to do something, right? Phosphorylation can occur by some mechanism, some other enzyme, which causes the protein, which causes the pump to become phosphorylated. That will eventually cause a situation where once this protein is loaded with 3 sodiums at its active site, right? We can also go into the crystal structure of the pump later. We might do that in the next video. Crystal structure of sodium potassium pump. That might be my next video. It's going to be one video down the road at some point. But when that happens, then the protein, which is normally closed from the inside, the carrier protein, right, will then change its conformational shape with the P, and then it will go, let's go to the new image, the discard, where am I going to save it? It will go, here's the cell membrane, it will go outside of the cell. Okay, so you have 2 protons here, not protons, you have 2 potassium here, potassium channels. You have 3 sodiums. The sodiums will be expelled, Na, and by expelling them, the charge increases outside of the cell, right? The amount of Na increases outside of the cell, so the concentration gradient, is worked upon, and as well as the electrical gradient. Okay, so I say electrochemical, it keeps slipping out of my tongue. Electrochemical refers to the concentration gradient and the electrical gradient together. Chemical and concentration are the same thing. I mean, these are all chemicals, right? Sodium is a chemical, potassium is a chemical, ATP is a chemical. So you have the concentration of chemicals, another shorthand way of saying it is the chemical gradient. Okay, the electrical and the chemical gradient are now in play here. So the electrical gradient is worked against. The sodium gradient, the concentration chemical gradient is worked against. Now, this is exported against its gradient. Potassium now also will be imported, because what happens is, as soon as sodium is exported, potassium attaches, and then the pump loses its P. Once it loses the phosphorus, the pump returns to its normal configuration, and it loses the affinity for the K positive ions. Those K positive ions then go back into the cell against its concentration gradient, right? Because remember, there's a large amount of potassium already in this cell. All right, so any more potassium that's taken from a pump or carrier mechanism is just going to increase the concentration gradient in the cell. Okay, and it's going to increase the it's going to go against the concentration gradient in the cell, because you're adding more to what is already a lot. It's also going to increase the chemical gradient, such that the electrical gradient, and then the electrical gradient will eventually cause the movement of these K pluses outside of the cell through the K plus leak channel. Okay, because once you build up enough K plus in a cell, right, it needs to get out, right? Because otherwise, if it didn't have a way out, you'd have a dielectric breakdown of your eventual dielectric breakdown, and like lightning would shock out of the cell. Okay, so you need to have a way for the potassium to exit the cell. Therefore, those channels, leak channels I was talking about before, are the perfect way to do that once the electrical gradient is large enough and the concentration gradient is large enough. But then this cyclic mechanism occurs over and over again. And this is basically through the use of these leak channels and these sodium input channels are one way the electrical cell membrane potential is maintained. So cell membrane potential is a very important thing to know, because all cells are electrically charged, and they're more negatively charged inside of a cell than they are outside, right? Despite the increase of like potassium, the large number of potassium charges, there's a large number of anionic amino acids and other types of negatively charged chemicals within a cell. So you can look up membrane potential when you get a chance. This video is getting way too long. Gone 20 minutes already. Not the longest video I've ever done. But again, this is all building, like you can tell, right? This is an example of negative across membrane, right? Positive charge separation. There's a lot of these large negatives A's in here. So, you know, cells are negatively charged, right? And so this is going to have to, there's always an electrical potential within a cell. You also have chloride ions too. I forgot about those. We're not going to talk about those now. Okay, that's it. I'll see you when I will.